So, okay, so welcome everyone to today's talk in the virtual symmetry and geometry with symmetries. So thank you for attending. So it's a pleasure to have Dennis Wulle today from the University of Münster, who will talk about cohomogeneity one manifolds with quasi-positive curvature. So thank you.
Yeah, thank you. First, let me thank you for the invite, for talking or presenting my research in this seminar. So let's jump right into it. So I first give you a short introduction on the topic, then talk about cohomogeneity one manifolds a bit, and mostly on the obstructions to quasi-positive curvature. And in the end, I will tell you a bit about the classification. All right. So what means quasi-positive curvature? So by quasi-positive curvature, we mean so Riemannian manifold has quasi-positive curvature if it has no negative sectional curvature, and there's one point with positive sectional curvature. And natural questions arises. So first is which metric or which manifolds admit metrics with positive or quasi-positive curvature, and is any of these inclusions strict? So positive sectional curvature, quasi-positive sectional curvature, or non-negative sectional curvature. So I mean, probably many of you know that in general you can construct. It's pretty easy to find examples, let's say, for non-negative sectional curvature, right? You can just take a compact Lie group and divide out the closed subgroup, for example, and you get a non-negatively curved manifold. And it's way harder for positive sectional curvature to find examples. And quasi-positive curvature sits somewhat in between now. So, right. So for non-compact manifolds, these questions are basically settled. So there's the Sow theorem by Chiga and Gromol that if you have a non-negatively curved Riemannian manifold, then there's always, which is non-compact and complete, of course. And then there's a totally geodesic submanifold S, the so-called Sow. And M is diffeomorphic to the normal bundle of S. Yeah? And if the manifold additionally has a point with positive sectional curvature, so it's quasi-positively curved, then Perelman showed that the Sow is just a point. Yeah? So M is actually diffeomorphic to Rn. And unfortunately for compact manifolds, it's different. Huh? So we actually, at least if we assume the manifolds to be simply connected, we don't know any obstructions for like to differentiate the classes of positive sectional curvature and non-negative sectional curvature. Yeah. Right. So the main goal is to determine these classes, maybe, but so the general problem might be too hard, so we restrict to symmetry assumptions. Yeah, and the symmetry assumption I want to make in this talk is so-called cohomogeneity. So we say that a manifold has cohomogeneity R if the orbit spaces are dimensional. Yeah, and I mean, you might know this from homogeneous spaces. Yeah. A connected manifold has cohomogeneity 0 if it is a homogeneous space. So in this talk, I want to talk about cohomogeneity one manifolds. So in this sense, it's those are the most symmetric manifolds after homogeneous spaces. All right. So for positive sectional curvature, I wrote down some examples. You don't have to read all of these slides. I just wanted to show you that at least above I mentioned 27, the only known 24, not 27. The only known examples in positive sectional curvature are the compact rank 1 symmetric spaces. No? So SN, CPN, HPN, and CAP2. Now, another interesting class of examples are the Eschenburg spaces, which are certain biquotients of SU3 by S1. And the Bazaikin spaces, which are biquotients of SU5 by SP2 times S1 action. Right. Okay. So for quasi-positive curvature, there are also known a lot of examples. For example, all Eschenburg spaces have a metric with quasi-positive curvature. Many of the Bazaikin spaces. And there's another very interesting class by Wilking, which, so the projective bundles of RPN, CPN, and HPN also admit matrices even almost positive curvature. Yeah? So there's even an open and dense set which has positive curvature. And the interesting thing about this is, so the dimensions of these, of course, go to infinity, right? And they are of cohomogeneity 2. So they are cohomogeneity 2 actions of ON, UN, and SPN on these bundles. And so a natural question to ask would be, is there any kind of this series maybe also in cohomogeneity 1? Or does this phenomena only occurs from cohomogeneity 2? So, and I mean, at least in positive sectional curvature, you can answer this with no. Actually, in any, basically in any cohomogeneity, this cannot, it cannot happen like this, but let's restrict to cohomogeneity 1. So if we have a positively curved cohomogeneity 1 manifold, then there's a classification by Verdiani, Grove, Wilking, and Ziller. So Verdiani did the even dimensional case, and Grove, Wilking, and Ziller did the odd dimensional cases. In even dimensions, we know that in positive curvature, so in positive curvature, that M is equivariantly diffeomorphic to a compact rank 1 symmetric space with a linear action. You know? In odd dimensions, it has to be one of the following spaces. It's either a sphere with a linear action, it's not very surprising, I guess. Then also it could be one of the Eschenburg spaces. Yeah, so not all. I mean, not all of the ones that I showed you earlier, but some of them are of cohomogeneity 1, and the whole series except for one of them has positive sectional curvature. And also it could be one of the Bazaikin spaces, which are somehow analogous. And it could also be one of certain 7 manifolds called PK or QK. And those are certain cohomogeneity 1 manifolds by S3 times S3 action. Yeah, I won't give you the details on how they look like, they're just part of this classification. So we know in any of these, of course, in any of these spaces here, we know that the sectional curvature is positive. Here for these, we don't know. So we know that P1 has positive sectional curvature. P2 has positive sectional curvature, and Q1 has positive sectional curvature. But this P1 is actually in a 7 sphere, and Q1 is in Alof-Wallach space, so they were known very well that these have positive curvature, right? P2 was is actually an exotic right, it's so it's homeomorphic to the unit tension bundle over S4, right? But not diffeomorphic. And okay, so I mean, you have seen there are some gaps here in the theorem, so they will be filled now. So if you assume just to have quasi-positive curvature, yeah, only two new examples add up to that list, which are the basically the missing homogeneity one Eschenburg space, which just has quasi-positive, or actually it has almost positive sectional curvature, and the and then analogous Bazaikin space, which has almost positive sectional curvature. And that's it. So otherwise, the list is basically the same. No? We still don't know if PK and QK for higher case have quasi-positive curvature, but so the original list by Wilking, and Ziller doesn't change up to these two spaces. Yeah? All right. Are there questions up to this point? Okay. All right. Now I'll tell you a bit about homogeneity one manifolds. So, we assume M to be a compact homogeneity one manifold with finite fundamental group. This essentially means that the quotient space is an interval, and we scale it to -1, 1. So we we call pi the projection map, and b plus minus to be the which are the inverse images of the boundary points. Those correspond to the non-principal orbits, and if they have lower dimension than a principal orbit, we call them singular orbits. Right. Then we pick a horizontal geodesic or a minimal geodesic between b minus and b plus. This will also be a so-called horizontal geodesic because it's orthogonal to any orbit. And by k plus minus, and we denote the according isotropy groups at the non-principal orbits, and by h we denote the principal isotropy group. And this structure, so you have to note that k plus minus, if you divide out h, then it is a sphere, and this allows us to write M as a so-called double disk bundle. So you can pick two tubular neighborhoods around the singular orbits and paste them together to a manifold, because their boundaries are both diffeomorphic to G mod H, and this gives rise to this so-called group diagram. So essentially, if you have a group diagram like this, so you have these four groups G, and which contain K minus, K plus, and H, and K minus modulo H, or K plus minus modulo H are isomorphic to spheres, then you could always cook up a homogeneity one manifold by gluing these together to this double disk bundle. And so essentially, so this is very good for us because we want to classify homogeneity one manifolds with quasi-positive curvature. So what we have to find is obstructions to these group diagrams. Now, of course, there are some equivalences among these group diagrams. For example, you can always interchange K plus and K minus, right? This shouldn't change the manifold. You can conjugate all groups by an element G. This just means you move the horizontal geodesic we picked earlier. And what you also can do is you conjugate one of the singular isotropy groups with an element in the normalizer of H. So this will also give the same manifold up to equivariant diffeomorphism. All right. So one last important thing that I want to mention is the so-called Weil group, which is which will play a role later in the classification. It's basically the stabilizer group of the horizontal geodesic, and it's generated by two involutions, W minus and W plus. And those involutions are unique in the normalizer of H intersected with K plus minus, at least up to H, they are unique. Okay. Good. Are there questions up to this point? Okay, great. So let me talk a bit about obstructions to quasi-positive curvature. So for the rest of the talk, we will assume that we have a complex Lie group G that acts by cohomogeneity 1 on a simply connected quasi-positively curved manifold M. And we denote the group diagram by H, K minus, K plus G, and by B plus minus the non-principal orbits. So for the rest of the talk, this will be fixed. And so our proof is basically very similar to the proof of Grohe, Wilking, and Ziller. Yeah. And they had certain obstructions already given to positive curvature, which is a so-called, I will tell this later in more detail, but one of them is rank lemma. So the rank lemma, so you might know that if you have a torus action on a positively curved even dimensional manifold, right, then the torus needs to have a fixed point. Yeah, so we can say something about the ranks of the isotropy groups of the G action. Yeah. Then there's also something called primitivity. This in some sense states that the group diagram is actually maximal in a certain sense. We have the chain theorem by Wilking, which basically says if you have a classical Lie group acting on a positively curved manifold with certain properties, then it's actually homotopy equivalent to a cross. And in cohomogeneity 1, this homotopy equivalence in the sense then means it's equivalently diffeomorphic. Right, then we in positive curvature we also have a classification of fixed point homogeneous manifolds by Grohe and Ziller. And this can, of course, now if we find a sub-action of our group action, which is fixed point homogeneous, we can use this classification, and then we are basically done, right? So once we have to establish this, we don't have to continue, right? So once we find an action like this, and the last obstruction, which was used heavily by Grohe, Wilking, and Ziller, was that there's positive curvature at the singular orbits. And so in the quasi-positive curvature case, the question is which of these obstructions are still valid. Yeah. And so the first four are still valid. So we still have some kind of rank lemma. Yeah. The proof just works very different. We still from this we can also from this proof we can also still follow that primitivity holds. Yeah, we still have the chain theorem. Also, we renamed it to the block theorem because in this case it was fitting a bit better. Then there, at least in the cohomogeneity 1 case, we can also say something about fixed point homogeneous manifolds. So these obstructions more or less still work. I mean, we had to work to establish them, but they still can be used. But the last obstruction it just failed. Huh? So there wasn't a good substitute for this. But still the classification works pretty similar. Just in the low dimensional cases, you had to be more careful and find other ways to prove to rule the group diagrams out. Okay. So now I will tell you a bit more detailed about the obstructions. So the first one is primitivity lemma. Yeah. So basically it means that so there are two kinds of primitivity. The first one is linear primitivity, and linear primitivity means that the Lie algebra of G is generated by the Lie algebras of the non-principal isotropy groups along the horizontal geodesic. That's why we have to conjugate them by elements of the Lie group of the Y group to move them. So it's not just generated by K plus and K minus, right? But it's generated by I mean, by any time the horizontal geodesic hits one of the non-principal orbits. And from this linear primitivity, we can actually get the following bound on the Y group. I mean, it's not, for this talk, it's not important what the actual bound is, but of course in the classification it is, because they are also, you can also prove upper bounds on the Y group, and then you can get contradictions using this, for example. And you can also prove that the Y group has to be finite. No? And another thing is the so-called primitivity. So primitivity means that not only K minus and K plus generate G, this would also follow from linear primitivity, but for any G in the normalizer of H, K minus and the according K plus generate G. Yeah. So this means for any possible group diagram, you could pick basically the isotropy, the non-principal isotropy groups would generate the whole group G. Okay. So, all right. And the other obstruction is the rank lemma. So the rank lemma gives a natural distinction between the odd and the even dimensional case. So in the even dimensional case, we know that there's at least one singular or non-principal isotropy group which has co-rank 0, so it has full rank in G, which is good because there's a classification of full rank subgroups of compact Lie groups, and the principal isotropy group has co-rank 1. In odd dimensions, we know that there's one isotropy group with co-rank at most one non-principal, and the principal isotropy group has co-rank 0, 2. Okay, so I will say a little bit about the proof. So the proof goes basically through this lemma. This was also for positive curvature. This was also proven by Grobe, Wilking, and Ziller. But for quasi-positive curvature, there were some problems in the proof. So this Call-Y lemma, it says if you have if G acts on a positively curved or a quasi-positively curved manifold and the principal isotropy group is trivial, then what we first get, we get that the order of the Y groups divides this number, but maybe more. What's also very important, we can say which groups can actually act in these cases. Yeah, so that we know the identity component of G, and you note that these groups are all of rank at most 2, right? And the reason for this is the rank lemma, because in positive sectional curvature we already know the rank lemma beforehand. Yeah? In quasi-positive curvature, this is not the case. We have to make a workaround and first prove this lemma, and then we know, okay, if at least if H is trivial, then you can then you have at most groups of rank at most 2 acting, and then you can make a reduction to this case and actually show the rank lemma for quasi-positive curvature. Right. So, I also wrote the proof here. So we start with the maximal torus in H, and consider the action of the normalizer of the torus to a fixed point component. Yeah. This was Dirac with cohomogeneity 1. And finite principal isotropy group. Now, if the isotropy group is trivial, we know from the Core-Y lemma that the rank of the group actin is actually at most 2. So we are basically done. This shows the rank lemma. And otherwise, we just pick we just make another reduction. We pick an element in the principal isotropy group. It should be H prime here, and the principal isotropy group, and act on the fixed point component of this. And of course, the new action has an even smaller principal isotropy group. So by induction, this result follows. Okay, now we'll say something about the proof of the Core-Y lemma. So actually, this was part of my master's thesis back then, to prove this lemma. Right, so we have a we assume that H is trivial in the Core-Y lemma. So we first prove another lemma, which is that if H is so the principal isotropy group is trivial, then we can show that the involutions which generate the Y group actually commute. So this means the order of the Y group is 4, at most 4. So the proof goes like this: we pick an element which is close to the identity, and so an element of G which is close to the identity, and we can also we can then find a metric which is close to the first metric, which also has quasi-positive curvature, but the horizontal geodesics now connects the point P minus in the which is in the non-principal orbit B minus to GP plus and not just P plus. Okay, but what does it mean? This means that this metric still has quasi-positive curvature, so this means the order of the Y group is finite, but we now have a new Y group which is given by which is generated by omega minus and the conjugation of omega plus by G, and this is still finite. Now we can embed this into some UN, and there we can actually show that that the order is constant. But then we are basically done, because we can now pick any G in G, and to move W plus and W minus to the same maximal torus, but then they commute, right? So this basically proves the lemma. So how do we use this? So by linear primitivity now, we can linear primitivity actually gives us now that the dimension of G is just bounded by 2 times L minus plus L plus, and the rank of G is bounded by L minus plus L plus. So L minus and L plus are the dimensions of the normal spheres. And then we can now just look. I mean, we know that if H is trivial, right, then there are not so many cases or so many options for K, because this is a sphere. But H is trivial, so this is also K plus minus. So we can only have that this is Z2 S1 or S3, right? And this means that L minus and L plus are bounded by 3, and then there are not so many D groups fulfilling this, so we can rule them out one after the other. Okay. Are there questions up to this point? All right. So now I move to the next obstruction. This is the block theorem. So the block theorem basically states So if G has the following form, so it has a normal factor which is isomorphic to a classical Lie group, and additionally the principal isotropy group contains a lower block. Yeah. So we have these matrices which are D times D, right? And we have this K times K block here. Yeah. And this K times K block, this needs to be contained in H. And so there's a small thing about K. So K should be at least 3 if we have SOD or SUD acting, and it's enough if it's at least 2 if SPD is acting. No? And if this is fulfilled, then M is equivariantly diffeomorphic to Sn, Cpn, or Hpn with a linear action. Now, Wilking basically has shown this the same theorem for positive curvature, but he didn't have the assumption that G acts with homogeneity 1. He has just had the assumptions SOD, SUD, or SPD are acting with this and containing this block, and then he could show the manifold is homotopy equivalent to one of these crosses. And right, but Wilking's proof doesn't work in our case, unfortunately. So for quasi-positive curvature, we have to find a workaround. And we found the following. So, right, so the first thing you have to prove is the so-called block lemma. And so if M has the same, so we have the same assumption as in the block theorem, but now the action is by cohomogeneity R. Yeah, so you could make this more general than cohomogeneity 1. And so we pick K maximal such that H contains a block BK. And then we could show that D minus K is bounded by R plus 1, right? So this means if you have a very low cohomogeneity, the block must be very large, right? So for example, if you have cohomogeneity 1, so the block must be at least must be at least of size D minus 2. You know? And right for in the homogeneous case, so if R is 0, this was already proven by Wilking and Ziller in their 2019 paper, where they revisited positively curved manifolds with which were homogeneous. But yeah, we could generalize this to cohomogeneity R. Okay. Right. I will tell you something about the proof later because it's a bit lengthy. Okay, now for the obstructions to fixed point homogeneous manifolds. So we could show that if you assume that there's a subgroup of G which acting fixed point homogeneous, and you have quasi-positive curvature, of course, then M is equivariantly diffeomorphic to a cross. And so the proof of this is essentially very similar to the proof of Wilking and Ziller, right? So their proof relied if you have a fixed point homogeneous manifold, then the orbit space is an Alexandrov space with boundary, and if it has positive curvature, the set of maximal distance from the boundary is just a point, so it must look like this, right? So this is just a point. And in quasi-positive curvature, unfortunately, this is not known, but in at least if we have the surrounding cohomogeneity 1 action, there's a very large set which has positive curvature, because like the orbit just moves, as the action just moves everything around. And this in this case, it means that this is enough to get this that this set at maximal distance is just 1 point, and then you could applies the same proof as Wilking and Ziller. Okay. Now this method actually allows us to reduce the actions to so-called essential actions. So we call them action essential if they if it contains no fixed point homogeneous subactions and no orbit equivalent subactions. So orbit equivalent means it has a subgroup with the same orbits. Okay. Good. So I already explained this. So we will now talk a bit about the proof of the block theorem. So we first start with the proof of the block lemma. So we can, of course, assume that P is a regular point because positive sectional curvature at one point is an open condition. And so we now pick this regular orbit, and by the slice theorem, the small tubular neighborhood around this orbit is isomorphic, is diffeomorphic to G mod H times slice SP. And now we pick a bi-invariant metric on G and split the Lie algebra of G in H plus Q. So this is the direction of this is the algebra of the principal isotropy group. And we now find self-adjoint operators Px that have such that as a Riemannian metric on G mod H is given by Q of Px. And now the strategy is that we compute the curvature of the principal orbit by using the Gauss equations, where this 2 is the second fundamental form, and R prime is the intrinsic curvature of the of GP, also of the orbit. So first of all, you can show this was done by Wilking and Ziller already in the homogeneous case, that if you have two commuting eigenvectors x and y of P at P, then the intrinsic curvature there is 0. So what we will do, so if we find these commuting eigenvectors, this part is 0, right? So we have to take care of the other two parts here. And this goes as follows. So we will find d minus k pairs of xi and yi of eigenvectors of pp, which commute. Yeah, it's first condition. And also it will. So the second fundamental form of xi and yj will vanish for if I is not equal to j. No? And the third condition is they will map to the same. So xi and yi will map to the same element vi, no? In the normal space. And if we have these conditions, of course, this guy vanishes. This is 0. This is 0, right? And this here is positive, because the sectional curvature is positive. So, but then we have d minus k vectors which have pairwise negative scalar product, but the normal space is just r-dimensional, and they are just, so in an r-dimensional Euclidean space they can only exist r plus 1 vectors with this property. So d minus k must be r plus 1, right? Or this is because we have a vector here and it has a negative scalar product with another vector. There can only be a third one, which has also negative scalar product with the other two, but that's it. We cannot add a fourth one here or something. Good. So how do we pick this? So if we so it can be shown that the block must be normal in the principle. So the k times k block must be normal in H in H, and so the normalizer of this block is given by, so at least the orthogonal complement of this is given by the set. Yeah, so you have basically here in these rows you have the standard representations of the block BK on k to the k, and we just set xj to be E1j, and so E1 in the j's row. So in the j's row here we would have 1 0 0, and yj would be just a E2 in the j's row. And this actually has the desired properties. So you can you can easily see check. Yeah, you can easily see that they commute. Yeah. Now we have to see that they that this one is 0, but this actually follows by an equivariance argument, because the projection to each row is just multiplication by some element in k. So k is either R, C, or H. I think I forgot to say this, but yeah. And then this term here is 0, because we were also gone in the sense before. And yeah, so these have the desired properties. Okay, but given this, we can now prove the block theorem. So I won't prove the whole block theorem because it's very long, but I decided to give you a few parts of it because it's very similar to the rest of the classification. So you have to do similar stuff, but it's quite it's easier to understand. So let me remind you, we're in the situation G is L times GD, where GD is a classical Lie group, H contains a block, and we have the group diagram HK minus K plus. Okay, so by the block lemma, we know that the block is very large, so D minus K is at most 2, and it's actually enough to consider essential actions by the obstruction of fixed point homogeneous manifolds, which we talked about earlier. So we can assume D minus K is actually 2. So this is good. This reduces our group diagram quite a lot. So we can assume that K minus is actually BK plus 1 times another group K minus bar, and H is actually H bar times BK. Yeah? So we will now only consider the K as SOD because it's the simplest of these, and I thought it would be most fitting for the talk. So yeah. So in this case, I mean, we know the classification of homogeneous spheres, and from this you can easily read off that this K minus bar needs to be in the ineffective kernel of the action of H on the sphere. So we know that K bar minus is actually H bar. So there are two cases. The first one is that the action of BK degenerates in both spheres. That means that it's not in the ineffective kernel of one of the spheres. And right, so in this case, we have that K plus minus are both mod H are both isomorphic to SOK plus 1 mod SOK. And this means K plus minus both have to be SOK plus 1. The reason is you can show from primitivity that the ineffective kernels of H on the action if H is acting on SL minus and SL plus, that these ineffective kernels have to intersect in a finite set. This reduces. This means that k plus minus both have to be SOK plus 1. Yeah. But now we are in the lucky case that the upper 2 times 2 block, which is in the normalizer of H, H is now SOK. Yeah, so it basically looks like this. We have 2 times 2 here, and here's the k times k block. Yeah, and this upper block is in the normalizer, and it acts on these basically transitively on these representations here, and this means that it acts transitively on the embeddings of SOK plus 1 containing this lower k times k block. So we can pick one, we can pick a G in this upper 2 times 2 block to make k minus and k plus the same, and this contradicts primitivity, because by primitivity this cannot be. They have to generate the whole group. So this case is ruled out. In the second case, we assume that the second case is that BK only degenerates in K minus. So there's not so many options for the other sphere, right? So this basically means that K plus needs to be where we have it. So K plus needs to be K plus bar times BK, and K plus bar needs to be S1. There's no other option. And there's only, now the question is only are K minus and H connected, or are they not connected? And you can so if we assume they are connected, we can represent the one of the Y group elements by this diagonal element. And this basically maps K minus to itself, but then by linear primitivity, we can actually show that the dimension of G mod H is bounded by K plus 2, but we can also compute the dimension of G mod H with this, which is 2K plus 1, and this is a contradiction. So so this case is ruled out, and so this means that our group diagram is basically given by, so we have, right. So in case that L is S1, we have S1 times SO K plus 2. Yeah, this is G. K minus was, right, Z2 times SOK plus 1. H is K plus is S1 times, so diagonal is 1 times SO SOK. And H is Z2, sorry, Z2, not Z squared, times SOK. And this this action is so this is a tensor product action on S2K plus 3. Rather move this to the right. And if and in the other case, if L is trivial, of course we get basically the same, but we have G is SOK plus 2, K minus is SOK plus 1 times Z2. K plus is S1 times SOK, and H is just Z2 times SOK. So now, of course, we know how the group diagrams look on these on the crosses, right? So we have a list and we just look at it, and then we see, okay, it has to be this group diagram, so M must be either diffeomorphic to CP2K plus 1 or to S2K plus 3. Yeah. And this is basically how the whole classification works. Yeah, you have, of course, there's more to it, right? Because now we know, okay, now we have a lot of information. We know the classical Lie group is acting, you have to rule out many cases, but it's essentially that's how it works in the end. Yeah, you use all these obstructions to rule out the group diagrams. Now I will tell you a few words about the classification. So we have this natural distinction between the even and the odd dimensional case. And in the even dimensional case, we have basically two main cases to consider, which is G is not simple or G is simple. Now, the second case basically works as a positive curvature, at least like Wilking and Ziller, they give another proof in their paper on the even dimensional case. And basically, in the simple, if G is simple, then this works almost the same in quasi-positive sectional curvature. There are just a few cases where you have to do things a bit differently, but this is very minor. Now, the first case where G is not simple, you have to use some other ideas, but still working quite well. In the odd dimensional case, of course, if H has co-rank 0, this is kind of easy, because then all groups have full rank. If H has co-rank 2, you first have to do first have to do the case where G is not simple, then the low dimensional cases or low rank cases, and then you do some induction arguments to get the higher dimensional cases and the so you need some induction arguments to get the higher dimensional cases, but it's so this works out quite well. Of course, like the main difference was actually in the low dimensional cases, because we have this missing obstruction on positive curvature at the singular orbits, and but it's still as you saw, it still worked out. So okay, so that's all I wanted to say. Thanks for your attention, and are there any questions?
Thank you very much, Dennis. Thank you very much, everyone. So are there any questions for Dennis? So I have a quick question. So I mean, do you have any, I mean, if you don't consider the cohomogeneity one, but just a fixed point homogeneous manifold with quasi-positive curvature?
Oh, I've thought about this, and I didn't get anything. So I mean, so the problem is, right, the Sol conjecture is not known for Alexandrov spaces, right? And I hoped it might be easier if you at least have a quotient, right? Because this is in many sense, I mean, a large part of it is actually a manifold, right? I had the hope that you could prove something, but I wasn't able to. I mean, I thought about this for some time, but it didn't find out anything.
Oh, yeah. And sorry, in your classification, which are the ones that are new that don't? It was the, I mean, new in the sense.
So there's this so I mean, they were known to have
the
quasi-positive curvature before. So one is this right, these Eschenburg spaces of cohomogeneity 1. So an Eschenburg space is given by this biquotient, right? And I think they have 1, 1 P here, and Q is 0, 0 P plus 2, right? So where this means that SPQ is just diagonal of Z P and Z to the P, and diagonal of 1, 1 Z to the P plus 2. And if P is 0 in this, then This doesn't have positive curvature. It doesn't fulfill this positive curvature condition for the Eschenburg spaces, because I think it's that Pi is not contained in the minimum of the Qi and the maximum of the Qi, or vice versa. Yeah?
Mm.
And if P0, of course, you have 0 here.
Mhm.
Yeah? This is 0, and there's 0 here, so this cannot be fulfilled. But it's somewhat on the boundary of this condition, so it still has almost positive curvature.
Mhm.
Yeah, and that's similar for the Bazaikin space.
I see. Okay.
So those are the only two. Of course, we don't know for the PKs and QKs, because they are just not known if they have quasi-positive curvature metrics or not. So.
Mhm. Okay, I see. Okay, thank you. So, yeah, are there any other questions? So, if not, well, thank you very much, Dennis, again
Yeah, thank you too.
for the talk, and thank you everyone for joining the seminar. And see you next time. And I hope you have a nice day or a nice evening or or night. So thank you.